we're taking are the notes we're taking today a continuation of what we did yesterday?
Yes. So I just want to kind of tie what we did yesterday, kind of review that, go over one more problem looking at that. And then the plan is, if we have time, jumping into the next section, which talks about limits. And so yesterday we were talking about average rate of change. And so if you're looking at an average rate of change, you're choosing 2 points on a curve, and you are finding basically the slope between those 2 points. We talked about being able to get a instantaneous rate of change by making those points, if they were further apart, making them closer and closer and closer together. And so when we were taking that slope between those 2 points, we're pretty much getting the rate of change exactly at a point on any and we can do that at any point on a curve. So in the past, we've only been able to look at slopes as looking at a line, and now we're making it so that we can now look at slopes on any curve. And so basically, I just pulled this picture from your textbook. Just thought it looked like a good kind of representation of what's going on in here. And so notice here, when we're looking at the tangent line, basically what the tangent line is that it's a line that goes through the point where we're trying to find that instantaneous rate of change. And that point on that line, it's orthogonal. It's basically, intersecting here at a 90-degree angle. Okay. But basically, if you take this point Q, here, if we were looking at the average rate of change between P and Q, notice that that slope is 0. That's a horizontal line. And that would be a bad representation of what the slope is here at P. But as we move along this line, notice that the slope is going to get closer and closer to the same slope as our tangent line. The line, the 2 points that are joining, and when we're finding the average rate of change, the line that is joining those 2 points, we call that the secant line. So notice over here, this is where we were choosing a point on the right-hand side of the point that we're trying to find the slope of the tangent line. Here we chose a point Q to the left of P. And from there again, as you go along this line, you're going to get a better estimate with those points and the slope at a particular point. Okay, so let's look at an example. Okay, so we're looking at a following example. You're given a graph, and this graph is shown that it has accompanied the total distance S traveled by a bicyclist after T hours. Okay, so our vertical axis S, this is the distance traveled, and our sorry, did I just say horizontal? Our vertical axis S is our distance traveled, and our horizontal axis T is the hours that have elapsed. And so we want to estimate the bicyclist's average speed over the time intervals. And so first one says we want to look at what's happening over the interval between 0 and 1. So we want to find the average rate of speed, right, when they started to this point 1 here. And so we can look at these as points if we want. And so here, this point, well, at time 0, they haven't traveled anything, and their distance is 0. So we have a point at 0, 0. And then if we look at this point right here, when time is 1, look at how far they have traveled. Well, this would have been 10 miles, so they have traveled, and this is 20, so that's halfway, that's 15 miles. And so we also have a point at 1 hour, and then we have 15 miles. So we can look at this as our slope, or so we're looking at rise. Well, we rose 15, right? And we traveled over 1. And so the rate of change, so the rate of change of the distance, which is S, all over the rate of change in time. So this was 15 all over 1. And so keeping it kind of as a fraction makes a little more sense here because of the word problem. And so we're looking at a rate of change. So they're doing 15 miles per 1 hour. So that would be the average speed they were going here. So now let's look at between 1 and 2.5 hours. We want to find the average rate of speed in that time. So we're looking at 1, which is here. And so we have a point, again, at 1:15. And then 2.5 hours, that would be here. And so notice here, that was 2.5 as our hours, and our distance is 20 miles. So our change in our distance over our change in time. Remember, distance equals rate times time, right? And so our rate, our speed, is the same thing as distance over time, which we're kind of doing here. Anyway, so change in S, well, we can look at it this way, or we can use 2.5 minus, actually, no, sorry, 20 minus 15. So we've only raised or rose 5 miles, but the time that we traveled for 1 hour to 2.5 hours, that's 1.5 hours. Okay, so technically we don't really like fractions with decimals, and so I'm just gonna reduce this. And so a way to get rid of that is we can multiply this by a fancy 1. I know in order to make this a whole number down in the denominator, I need to move this over 1 spot. So if I multiply that by 10, this would give me a whole number. And so I have to, whatever I do to the numerator, I have to do the denominator. And so I get 50 over 15. So we really want to reduce. 5 goes into both of those. So we have 10/3. So they're going 10 miles every 3 hours is how this is expressing it. We could put this as a unit by dividing this in here. And so this goes in 3 1/3. So they're going 3 1/3 miles every hour. But that's the average rate here. Notice that average rate here is a lot. If I looked at the slope here, that slope of that line is a lot smaller, right, than the slope of the line when we looked at these 2 points. So it makes sense that that average rate of change in there was smaller. And so now we wanted to look at the average rate of change between 2.5 and 3.5 hours. So at 2.5 hours, we still have that point. So at 2.5 hours, they traveled 20 miles. And then at 3.5 hours, which would be right here. And so 3.5 hours, they have traveled a total of 30 miles. So from here, they went from 20 miles up to 30 miles. And so they rose 10 miles all over the change in time. So from 2.5 hours to 3.5 hours, that's just an hour. And so here they're going 10 miles per hour. So if you look at the slopes of these lines, you can tell that this blue line in here, this is steeper than this one in here. And our 3 1/3 miles per hour was our green, which was not as steep. Okay, so if you wanted to estimate the bicyclist instantaneous speed at t equals 1/2 hours. So I think I want to grab this or just erase this so I can go back and look at it. So for part B, we're looking at t equals 1/2. So let's go to 1/2 hours, and that would be right here. We're trying to find that instantaneous rate of change right there. And so a couple things that we can do. We can choose points that are really close to this and find out what the average rate of change is. Or we can think of this as our tangent line. So if I can draw it correctly. So when I'm kind of thinking of the tangent line and how I'm going to draw it on that graph, I kind of think about driving on this line in the evening and you have your headlights on. And so your headlights, those are going to be pointing in the direction when you're on the road of what your tangent line would be. So I just kind of imagine that car in here and my headlights are pointing this direction. So if I look at that line and I don't do it algebraically and I kind of look at it this way, we can think of rise over run. Let's look at 2 points on a line that, are whole numbers. So like right here and right here. So at this point, I can estimate what my average rate of change is. So at t equals 1/2, actually, it wants the instantaneous, not the average. My instantaneous rate of change, I am going to approximate. Okay, so I'm thinking here, I'm rising, so I have to see how much I'm rising. So from 10 to 25, I'm rising up 15. All over how much I'm running. And so I'm going from a 0.5 to a 1.5, so that's running over 1. So the average rate of change by looking at it that way gives us this.
Why are we going to 1.5 again?
I just wanted to draw what I thought would be the tangent line at this point. And so the tangent line would look like this. And so I just extended what that tangent line is. And I decided just to choose 2 points on that tangent line. This one seemed easier to me because it looked like it was intersecting at whole numbers versus like if I chose down here, I would have to kind of estimate. This is about 17. But right now we're just really kind of getting an estimate and not totally accurate. The other way that you could have thought of it is instead of making that tangent line there, we want to know at 1/2 right here, choose 2 points there. And so it looks like, one of our points, let's choose that point that we're looking at. So here, well, this is at 0.5. So we have a point at 0.5. And it looks like, it doesn't look like it's exactly 10. It looks like right below. So if I can estimate that, maybe I would say 9. Let's choose another point that's really close here. And so how about this point right here? So this point right here, I would say maybe this is about 0.7. So my X value is 0.7. And my Y value here is 10. So let's look at the slope between those 2 points, which is really close to the point that we're trying to find the instantaneous rate of change. And so if we look at the change in S, so that would be 10 minus 9. All over the change in our T value. Well, from a 0.7, 0.7 minus 0.5. So this is 1 over 0.2. Again, let me kind of reduce this. I can multiply this by 10 over 10. So this gives me 10 over 2, which is totally different than what I got over there. So again, I guess it's like an estimate, and it really attends to what points you decide to choose. Okay, so let me just pause real quick.
So when you drew in the tangent line, it was just a complete guess, I guess, something like that?
Yeah, exactly. So, you know, maybe I was off when I was drawing that tangent line, and this might be a little more accurate. So it might have maybe looked more like this or something. I don't know. And so it wasn't as steep. And so maybe then here, if this was the point here instead of what we set up there, this would have only rose 10 to 15. That would have rose 5. And then that distance would have been 1. We would have gotten the same thing. So I was a little off on where my headlights would have been pointing on that drive when I drew that line. So that's where it's a little more accurate if we're choosing points on that graph and choosing them really, really close to the point that we're trying to find that instantaneous rate of change. So that's going to be more accurate than what I had done when I was drawing that tangent line and being off on that. So that instantaneous, where do I just have that?
So is 5 the instantaneous rate of change for 1/2?
Yeah. Yeah, so 5. So they're traveling right there at, so what is this saying? So this is saying at a half an hour, their speed, that the instantaneous rate of change, that speed exactly at 1/2 hour is 5 miles per hour that they were traveling on their bicycle.
Okay.
So this here would have been just the rise 5 instead, and this would have been over 1. So the rise 5 over 1 gave us the same thing we had over here.
So as long as you used 1/2 as one of your points, you could choose any other point and got 5?
As long as I usually use the one point that they want the instantaneous rate of change at. So in this case, because it was 1/2, yeah, use that point. And then it depends. Choose either a point that looks really close to it, or try to determine how that tangent line would look at that point, and then do the rise over run to find that rate of change.
Oh, okay.
So maybe the next one we'll see if we can do it better this time. So like now they wanted the instantaneous rate of change here at t equals 2. And so if I go over here at 2, to me, if I was driving on this line right here, it looks like I'm almost, if not, a horizontal line. It might be increasing a little bit, but let's do it by choosing points. Okay, so the point, they wanted it at 2. And so at 2, there is a point, and it looks like that is at 220. So when t is equal to 2, we have a point at 220. And so we want to choose a point that's really, really close to that. And so either go to the left or the right of t equals 2 and choose a point and estimate what you think that y value is. And so in this case, you know, if I went out here, this is 2.5. So if I went out to, let's say, 2.2. So 2.2, we want to determine what we think that y value is there. And if you look at what that y value there, doesn't that look like it's pretty much the same, that 20?
Yeah.
And so if we think of that rise, well, we didn't rise anything. 20 to 20 is 0. So our rise is 0 all over our run, which we went from 2 to 2.2, so 0.2. Well, 0 over a number other than 0 is 0. And so basically this is telling us that while they were traveling on their bike, they stopped, they paused, they took a break. They didn't go any further. Their distance from where they started hasn't changed. So I'm gonna, if it's okay, skip part, well, actually maybe 3 is better. So t equals 3, maybe just do it. So go to t equals 3. It looks like it's a little bit above this 20. And so t equals 3. I have a point at 3, and I would say maybe they've gone 0.1 mile. So that's 20.1. Actually, 21. And we want to find a point that's really, really close to this. What about right before, I don't know. How about right before, right here, right when it looks like they started getting on their bike and traveling again? So if we did that, this was 2.5 hours, so maybe this is 2.9 hours. 2.9 hours, they just got on their bike and then they're gonna start riding their bike. And they were only at 20 miles. So if we look at rise, they went from 20 miles to 21 miles. So that's 1 mile. And the change in the time there, well, they went from 2.9 hours to 3 hours. That's 0.1 hour. So they're going about 10 miles per hour there. So looking at that graph, can you tell when they were traveling the fastest? Estimate the bicyclist's maximum speed and the specific time at which it occurs. So what do you think is happening in the graph when we're looking at the maximum speed in part C?
Probably 3.5 or like, yeah.
Okay, so why did you determine 3.5 as the maximum speed there?
Because it's the steepest slope.
Exactly. So when we were looking at this rate of change, we were looking at distance over time, which is the speed. And so and we're looking at the slopes on all of these. And so where it looks the steepest slope, you're right, it looks like at 3.5 or anywhere in here, right? And so let's say 3.5. I think it's 3.5. This might start to turn. How about here? Okay, so if we did it there, that's almost 3.5. So how about 3.4? So we have a point max speed. 3.4. And if we look at this, they're at 25 miles. Oops, didn't mean to close that. Choose a point next to that. And so maybe here at 3.5, we have a point, and that's at 30 miles. And so the change in our distance over change in time, we've traveled from 25 miles to 30 miles, that's 5 miles. And we've gone from 3.4 hours to 3.5 hours, so that's 0.1 hour. And so this will give us 50. That just seems really fast, doesn't it?
Yeah.
50 over 1.
On a bike.
On a bike. But who knows? They could be coming down a mountain and they could
Yes.
just be picked up so much speed.
That's true.
Yeah, I live on a hill, and people train on my hill all the time, and so there I could see them coming up and then speeding down, and I think they go faster than our speed limit.
Oh, probably.
So we could kind of reason, but maybe if we got like 250 miles there, we might be questioning. And you know, this is kind of good because we're looking at a problem. You kind of should be questioning your answer. Does that seem realistic and stuff? So
Yeah.
there's an example where we might have given some reasoning why that 50 miles per hour on that bike. So hopefully that example kind of tied some stuff together on the average rate of change versus instantaneous rate of change, which was the first topics that we looked at in this course. Any questions over that material?
No, ma'am.
I know, well, we have 12 minutes. 12 minutes is almost a quarter of our class. So let me jump into the next topic. And maybe, because I'm doing that, I'm gonna stop the recording and restart the recording.